Hey everyone, this is Mr. Mountjoy, and before we begin, I want to kind of just talk about something we're doing a little bit differently this week. We're trying out for Unit 3, which is we're going to do some of the teaching through video form and then give you a lot of opportunity in class in order to practice some of the things that you watched in the video. And that way, when you're doing your practice, you have myself and Miss Woodard there to help you out. So that's the goal of this whole process, is that you watch the videos and that you do some work before class. And then when you come into class, you're going to have the opportunity to get any questions you have clarified because you've already learned the content and now you're actually getting a chance to practice it. The first thing you need to do is on week 13 Desmos. This is going to be a Desmos for the entire week. And so what we want you to do is we want you to do the Engage and Explore and then watch this video and fill out your Desmos along with the video as if you were in class, okay? So the Engage and Explore are for you to be done on your own. So if you haven't done those yet, please pause the video. Go and fill out the Engage and Explore for week 13 Desmos. And then when you're done, come back to this video and then we will start going over some of the guided instruction. So if you haven't done it yet, please pause the video, go do that, and come back when you're finished. All right, so let's go ahead and get started. So the first thing I want to do is I want to talk about what does the problem actually tell us? What is the information that they gave us in this problem? So if I read this, it says, in 1990, Nigeria had a population of about 95.3 million. By 2000, there are about 122.4 million people, an increase of about 28.4%. During that decade, the population can be reasonably modeled by an exponential function. Okay, so what they just told me is a few things. So let me share what they gave us here. The first thing they told us is our starting population. So they said in the year 1990, we had 95.3 million people. So that's the beginning of our population. They also told us the end. In 2000, they had 122.4 million people. And the other thing they told us is they gave us a hint that this was an exponential function and that function had an increase of about 28.4%. So in green, this is a tip-off of what equation I'm going to use and the fact that I need to find the growth factor. They're giving us a tip that it's around 28.4% increase, okay? So we're going to have to translate that into a growth factor. And then they gave us the starting and ending position of this exponential model for the population of Nigeria. Now, they want us to do a few things with this info. So the first thing they say is a student said the population of Nigeria grew at a rate of 2.84% every year. So remember that our increase from earlier right here represented not over 1 year, but over 10 years, right? It was 28.4% increase in 10 years. They're saying that, well, that would mean that this is what the population is growing by every single year. So we have to compare those two and decide whether or not this is true or not. Okay, so that's kind of like something that we should start thinking about. Is a 10-year growth of 28.4% the same thing as growing 2.84% every single year? Okay, so they say explain or show why the student statement is incorrect. And that was a huge piece of information for us. Now we know that this statement is a lie. We know it's not true. So we're going to have to think a little deeper about this in order to figure out what's the deal with this yearly growth rate. Okay, so let's go ahead and think about what an exponential model would mean. Based off of our information over here, we know a few things. So what does an exponential model look like? So our function, let's call it f of x. Oh, let me actually go backwards. Let me think about what they said here. Earlier, they said that our function is in terms of decades. So we're going to think our function f of d, which is decades, okay, this is going to represent our exponential model, needs to have the starting place, so whatever the starting population was, times the growth rate raised to the decade. Okay, so this is what our function's going to look like. But A and B are going to be numbers, right? D is still our variable, but A and B are numbers that represent, A represents the starting population, and B represents the growth factor. Okay, so let's just take a quick note of that. A represents our start, so we'll call it starting population, and B represents our growth factor. Okay, so this information is all we need in order to write our function for this. That'll help us determine what's the deal with this student statement of a 2.84% growth rate each year. Okay, so let's go ahead and try and write a function here. So what do we know? We already know they gave us A right here. If I look at this problem, they said the starting population was 95.3 million people. They told us what A was already. So this is really nice. I can go ahead and fill that into my function. F of D is equal to 95.3 million times whatever the growth factor is raised to the decade. Okay? So now all I got to do is, in order to finish out writing an exponential function for this, is I need to figure out what B is. So how would I go ahead and figure out what B is? Well, there's two options here. The first option is just to divide over the decade. So I know at the beginning of the decade, so let's call B as our growth factor, if I divide what the population was in 2000, so I'll say the population of 2000 divided by the population of 1990, that would give me the growth factor for that one decade, right? If B is the growth factor for one decade, all I got to do is divide. So our two numbers were, the population in 2000 was 122.4 million, and our population in 1990 was 95.3 million. So what do I get if I divide these? If I just plug this into my calculator real quick, I'm just typing in 122.4 divided by 95.3. I get 1.284, and then it keeps going, right? But that's a good rounding spot. I've got 1.284, so that is, pretty decent amount of decimals. I could go on if I wanted to, but I'm going to round it there. Okay, so there would be my growth factor. I just got that by dividing. You might also do it this way, though. You might also say, well, hold on a second. They said that there was an increase in that decade of 28.4%. Well, how would we figure that this represents our growth factor as well? Well, we'd have to do it this way. It would be 100% of our population in 1990 plus the increase of 28.4% that we had over that decade, right? I'm just showing you a second way to calculate this growth factor. So if I turn these into decimals, 100% as a decimal is 1.00, and 28.4% is really 0.284. And if I were to add those two together, notice I get the exact same thing, 1.284. That's what I got earlier, right? This was the same amount, the same growth factor that I got earlier. And so I found it two different ways. The first way I found it was by dividing the population at the end of the decade by the population at the beginning of the decade. The other way I found it is by taking what percent of the population was represented in 1990, that was 100%, plus an increase of 28.4%. So if I add those two decimals together, I get the exact same growth factor, okay? So what does that mean for our function? Well, we can take what we had earlier and finish off our function. F of D is 95.3 million people times 1.284, that's our growth factor, raised to the d power, or to the decade, right? So this now represents our population's growth in Nigeria every decade. So whatever I plug into the variable d represents how much the population has changed over that time. All right, so now that we have that function, we can go back and think about what is the problem saying. So they said incorrectly that the population grew at a rate of 2.84% every single year, right? And they told us that was incorrect. So how could we figure out what did the population actually do over the course of 1 year? How would we figure that out? So first of all, we'd have to think back to our table in the Engage. If I wanted to represent 1 year, how many decades would that be? Okay, how many decades would that be in 1 year? So when we did that table earlier, you probably saw that 1 year was 1/10 of a decade, right? A decade's 10 years. So 1 year is 1/10 of a decade. So what we want to know is what was our growth rate for 1 year? What was our growth factor for 1 year? So the way that we can find this is we can think about what would we be multiplying by in order to find 1 year. So this is what we would get. If I did f of 1/10, right? This represents what is the population of Nigeria after 1 year. What we really have here is the starting population times something. And what are we multiplying by? We're multiplying by 1.284 raised to the 1/10 power. So the thing that we can use in order to multiply the starting population by in order to get the growth factor the population for 1 year is this part right here. If you do the starting population times this number, that is the growth factor for 1 year. That is the thing that you would multiply by for 1 year. So that student said that it was 2.84%. So let's find out what it actually is. So if I calculate this, if I do 1.284 raised to the 1/10 in my calculator, what does this give us? So I'm going to type in 1.284 raised to the 1/10 or 0.1. And so that gives me a growth factor of 1.025. Okay, so that tells me that my actual growth factor is going to be for 1 year is about 1.025. Okay, so if in answering this question, now we can come over here and say why this student was incorrect. So we could say, explain or show why the student statement is incorrect. The student is incorrect because the actual growth factor for 1 year is 1.025. Not what they said, which was 2.84%, right? Which would have been a actual growth factor. So what they're saying is if I were to put what they wrote in terms of a decimal, that would have been 1.0284, which is not what we were growing by. We're growing by 1.025. So they were a little bit off in what they were calculating, okay? So the way that we calculate what the actual growth factor is we plugged in right here what 1 year would be into our equation. And then we were able to figure out what was the number that you multiply by for 1 year. You would multiply by 1.284 raised to the 1/10th power. That is the growth factor. So how did they come up with that actual incorrect answer? What did they do wrong here? Well, if you notice, if you take what they gave us in the original problem, 28.4%, and if you divide that by 10 years, right, this gives you 2.84%. So what they incorrectly did, this is the incorrect way of calculating growth factor, is they just thought that they could divide evenly by 10 because there's 10 years. So to get to 1 year, you would divide by 10. This is how you would find a linear growth factor, right? If it's increasing by the same amount every year, that represents linear, but we don't have that. We have exponential. So this is our exponential growth factor right there, which is 1.284 raised to the 1/10th power. Okay, so I went ahead and I actually already calculated the correct growth factor because I used it in order to show that they were incorrect. So find the correct annual growth rate, explain or show your reasoning. So if I was going to correctly calculate this, what I would end up saying is, well, what percent were we growing every single year? So our annual growth rate would be what percent were we adding on to in order to calculate this. And so let's pull it up. We had our growth factor was 1.025, which represents a growth rate. So whenever they say growth rate, they're asking for a percentage. Growth factor is that 1.025. So if I want to convert this into what percent did we increase, well, you can see that here on the end, this represents 100% of the population, and this represents what we grew by, right? So what did we grow by? We grew by 2.5%, right? If I convert this part of this into a percentage, right? If I convert that part into a percentage, that'll give me what my growth rate was. So the actual growth rate was 2.5%. Okay, so we were able to correctly calculate the annual growth rate for this problem as 2.5%, not what the student originally thought, which was 2.84%. They thought it was growing a little bit faster than what we thought or what we found. And that was because they confused the exponential model with a linear model. They tried to calculate it by dividing by 10, but we know that we should have raised it to the 1/10th power, okay? So that's the difference between our linear and exponential functions, and that also is the difference between the correct growth rate and the incorrect growth rate. All right, so next up we have a problem from Miss Woodard. Make sure you're continuing to follow along. We have one more example, and then that will be it for the video lesson, and that'll have you prepared for our in-class lesson, which is going to be doing some practice problems, calculating growth rates, and writing exponential functions.
Okay, so hello everyone. We're going to start I'm going over the guided instruction for 4.3 got caffeine. So I'm going to start by reading the situation here. This one, oops. We're going to start by reading here. In healthy adults, caffeine has an average half-life of about 6 hours. Let's suppose a healthy man consumes a cup of coffee that contains 100 milligrams of caffeine at noon. So I'm going to pause here before I start reading the question. I'm just going to ask myself, what's happening in this situation? Well, those two sentences describe to me a person drinking a cup of coffee at noon. And when they do that, they consume 100 milligrams of caffeine. And then it also tells me that caffeine has an average half-life of about 6 hours. What a half-life is, it basically means that half of that caffeine is going to be, you're only going to have about half of that caffeine left after 6 hours. So this person drank caffeine at noon. They drink 100 milligrams at noon. So at 6 p.m., 6 hours later, they're only going to have 50 milligrams of caffeine in their system left. 6 hours after that, they'll have 25. So every 6 hours, we have half less the amount of caffeine. Okay, so let's think about that problem now. So number one, each of the following expressions describes the amount of caffeine in the man's body some number of hours after consumption. Question is, how many hours after consumption? Well, I'm looking at the 4 expressions given to me, and they all look really, really similar. They all have a 100, they all have a 1/2, but what's different is the exponent. So let's talk about where each of those things comes from. What is the 100 representing? Yeah, let's do it back. So 100 is telling me about how much caffeine. What was the starting amount of caffeine? When this person first consumed caffeine, they had 100 milligrams in their system. So what's that 1/2 telling me? 1/2 is telling me about the half-life of caffeine. It's telling me what the growth factor is, by how much is it changing every time period that's described. So for example, every 6 hours, it's decreasing, it's decaying by half. Okay, so then that comes to our exponent. So what is our exponent representing? Well, this is representing the time. After, we know that the half-life, we know that caffeine is decreasing by half every 6 hours. So it's this one in this situation is representing that 6 hours. We know that 1/2 of what's left is going to decay after 6 hours. So this is, this tells us how much caffeine is lost after that time period, 6 hours. So I know 1 is representing 6 hours. Okay, so I know the half-life will change every 6 hours. It'll decrease by half every 6 hours. So then we go to the next one where the exponent is 3. Well, we know that 1 is representing one time period, one time frame is representing 6 hours. So if I now have 3 of those, what's 3 times 6? That gives us 18 hours. And then the next exponent is 1/6. So this is now a fraction. This is now telling us it's not a whole time frame. It's not our whole time frame of a half-life, but we can still multiply by 6 hours and get 1 hour. So if the exponent is 1/6, then we're only talking about 1/6 of the time period, which is 1 hour. So then that brings us to T. What's T representing? Well, we already know. T can be, it's a variable, so it can be replaced with anything. So it really depends on what time period are we looking at. Are we looking at 10 hours after this person drank caffeine? Are we looking at 24 hours after this person drank caffeine? 4 time periods, 3 time periods, 2 time periods, 1 time period. T is replaceable. So T is just representing time. Anytime. So then I'm going to look over at this table on the other side of the screen. Oh, if you haven't been doing so yet, you should be following along on, I forgot what screen number this is. Oh, screen 5. I'm on screen 5. So you should be typing notes on screen 5 to help you remember all the steps that I'm taking. So now on this screen 5, we're going to be filling in this table. So if this expression had an exponent of 0, how many hours would that be representing? Well, how many hours are in one time period? We said 6 hours are in one time period. But if we have 0 time periods yet, there's 0 hours. So how much caffeine? Well, we can use that same expression, right? Because we said basically we are replacing this T right here with however many hours we're looking at, or yeah, however many time periods we're looking at. So if the exponent's 0, we're looking at 0 time periods. So I'm going to replace T with 0. And if I was to actually evaluate that, anything to the power of 0, 1/2 to the power of 0 is just going to be 1. So 100 times 1 is 1. 100. 100 times 1 is 100, which tells us 0 hours after he drank that cup of coffee, he had 100 milligrams of caffeine. So far, this is matching up. So then our next exponent that's given to us is 1/6. So how many hours is that representing? So that's representing 1/6 of the time period, and each time period has 6 hours. So this is representing 1 hour. And so notice we're not actually putting in 1 hour as, we're not putting in 1 as our exponent, because the exponent is representing the time period, the half-life of 6 hours, after 6 hours, because we know that caffeine will decay half the amount every 6 hours. It's not going to decay half the amount in 1 hour, it's every 6 hours. And the expression given to us has a 1/2. And we know it's the caffeine, the milligrams of caffeine is going to decay 1/2 every 6 hours, not every 1 hour. And that's why we're representing 1 hour with the fraction 1/6. All right, so then if our next exponent is 1, we know that's representing 6 hours. That's told to us that's the half-life. If we have an exponent of 2, well, how many hours is that? Each time period has 6 hours, so this now is meaning 12 hours. And how would that look in the expression? We still have the same amount of starting caffeine times 1/2 the growth factor. And now we're talking about 2 time periods. So then our next exponent is 3. So we have 3 time periods, each time period lasting 6 hours, and we get 18 hours. Okay, and then T, well, we've already talked about T. T is a variable. It can be replaced with any number really that we're looking for. It just depends what time frame we're trying to look at. So T is representing T hours. So then we move on to the next slide. No, wait, let me zoom out. I'm going to pause here. The great thing about these guided instruction videos is that you get to pause this, rewind it, listen again, listen to it as many times as you need. So if you need to pause the video here and go add your notes to Desmos. And I'm going to take us now to screen 6. So on screen 6, we have two more questions. So on this screen 6, we're asked to write a function g to represent the amount of caffeine left in the body h hours after it enters the bloodstream. So this function is going to be g of h, right? We're told to write a function g, and we're going to be using h to represent hours. So I'm actually going to look back at the previous screen really quick and remember, let's do this. And remember that this expression right here is telling us about a 6-hour time period, but we want to break it down and look at it hour by hour so that we can determine how much caffeine is there after 1 hour, how much is left after 2 hours, after 3, and so forth. So I'm going to be using the expression that talks about how much caffeine is left hour by hour. And that's the 100 times 1/2 to the power of 1/6. So remember, 1/6 is representing just 1 hour. So we're going to take that, that's going to be where we start. So 100 times 1/2 to the power of 1/6. So again, this is talking about one specific hour. If I want to know about 2 hours, 3 hours, 4 hours, 5 hours, 7 hours, 6, however many hours, what am I going to be trying to essentially replace in this equation? And so remember, what we've been doing so far is multiplying the exponent by one time period. So we know one time period has 6 hours. So this exponent right here is telling us about 1 hour. So if I want to know about 2 hours, I could be changing the I could change the numerator into a 2. And since the denominator clears by multiplying that by 6 hours, I'm left with 2 hours. If I change it to 3, if I change the numerator to 3, I'm left with 3 hours. So then I'm going to be wondering how, this would be the quickest for me. So I want to know, how can I make sure that the numerator in this exponent is always going to represent however many hours I'm looking for? I want it to represent h hours. How am I going to get the numerator to represent h hours? I can do that by just adding an exponent of h. So if I want to know what the half-life is, how much caffeine is left after 2 hours, say g of 2, I can just replace oops, I left out the 1/6. So 1/2 to the power of 1/6, and replace it with a 2. That's equal to 100 times 1/2 to the power of 2/6, or 1/3, which is still representing 2 hours out of 6, my 6-hour time period. If I replace G of 3, I will get 100 times 1/2 to the power of 1/6 to the power of 3. So, and that will give me the time period for 3 hours. And then whatever I replace H with is representing the hours. Okay, so then we go to the next question, 2b. The function f represents the amount of caffeine left in the body after t 6-hour periods. Explain why g of 6 is equal to f of 1. So it's telling us the function f represents t 6-hour periods. So this, where we want to know, why does g of 6 equal to f of 1? Well, what does f of 1 mean? They told us that's representing 1 6-hour period. So f of 1 is talking about 6 hours. Well, what's g of 6 talking about? We know that the h is representing hours. And so in this case, if h is replaced with 6, it's talking about 6 hours, because h is equal to 1 hour. We're replacing h with 6, so we know it's 6 hours. So g of 6 describes how much caffeine is left after 6 hours. F of 1 describes how much caffeine is left after 1 6-hour period. And there you go. In case you can't read my writing, I said G of 6 describes how much caffeine is left after 6 hours. F of 1 describes how much caffeine is left after 1 6-hour period. So they're both describing 6 hour, let me add that, they're both describing 6-hour periods. They are both describing 6 hours after, after caffeine enters the body. And that's it for 4.3, got caffeine. Make sure to add notes on your Desmos, and come to class tomorrow with questions.